Hi, everyone. Um, so, so just to kind of get started, I wanted to share with you some kind of to frame kind of what we're going to be doing here, just to do some test taking tips. The one thing that kind of makes AP Physics different than like a normal high school class is knowing all the processes and skills that are being tested as well, right? Normal high school class, you would just kind of learn you just kind of learn the concepts for physics. You'd learn, the equations and stuff and how to use them. But the AP test really tests in a much different way. And so, depending on your high school teacher, you may not have experience with that. Some teachers like to do very AP style questions, AP style thinking, but some teachers don't. Some teachers teach AP Physics more like just a regular high school physics course. And so people can come into it at different levels with different levels of understanding as far as those specific skills for solving physics problems, which is very important. Your test score is going to go up for sure if you know how to answer the physics questions in the way that the AP test wants you to answer them versus just knowing how to solve for a number, which is going to be a problem if that's the only kind of physics experience that you have. Talk about when you're solving, especially the free response questions, you want to be asking yourself where are the points, the amount of points that are available on a question. Some of the free response questions are worth 7 and some are worth 12. You don't need to get you don't need to get all 12 points, let's say, on one of the long free response questions. It's a matter of how do I go through and pick out as many points as I can? How do I demonstrate what I know in order to earn as many points as possible? I try to tell students that, on a 7-point problem, you should try to get at least 5 points, because 5 points will correspond to basically a 5 on the AP test. If you're able to go through and, obviously you want to get all the points you can. But it's a matter of a new way of thinking and a new way of solving these problems. So let me give you some examples of how we would go through and do that. So first off, I have a multiple choice question here. So half the points, are for multiple choice questions. The questions are more conceptual than you may be used to. They're longer questions than, like, say, even like the physics C test multiple choice questions. Aren't as just much reading and selecting both in the prompts and in the answers. So this question is actually about average, for AP question length. If you haven't seen practice questions like this, they like to do comparisons. So you see here, like, they say, okay, the diagram above shows a top view of a child of mass M and another platform of mass 5M. So they won't usually give you 10 kilograms and 15 kilograms and stuff like that. They'll usually give you some kind of comparative value, whether that be M for mass or R for radius or D for distance or whatever. They'll give you some kind of comparative mass and then something that's 5M or half M or something like that. And so you still have to use those reasoning skills, but it's not in terms of concrete numbers as much as in terms of kind of a theoretical, single mass. And then so when we go through and we have to make sure that we read through these questions and analyze them, because a lot of times there are, I don't want to say trick questions, but they're looking for a specific type of understanding. So as we read through this, so it says, assume the platform rotates without friction. Which of the following describes an action by the child? Okay, so they like to deal with systems of objects and such. So it makes a big difference whether the action is by the child or by somebody standing next to the circular platform. It makes a big difference as to how the angular momentum is going to change in this case. And then it says that will result in an increase in the total angular momentum of the child platform system. So the child platform system includes the child and the platform. And that makes a big difference in how we answer the problem. If we're talking about increasing the child's angular momentum, increasing the platform's angular momentum, or increasing the angular momentum of both the child and the platform. And so what they want you to know in this case is that the child platform system, because the system includes both of those objects, right? That means that you would need to be outside of that system. So you would need to be a person standing beside the circular platform in order to change the momentum or the angular momentum of that system. The child could change its angular momentum, like the child could move out and gain angular momentum, and the platform would lose angular momentum, or vice versa. But the child cannot, by doing an action on the circular platform, change the angular momentum of the whole system. And so that's the kind of reasoning that we have to go through on these problems. And so you have to look for key terms like, oh, child platform system. Okay, the child is acting on the child platform system. That means that it's going to be that means the angular momentum is going to be conserved. So as we read through our answers, we see, okay, D is none of the actions described will change the total angular momentum of the child platform system, because the child can't do anything. It would have to be an outside force of some kind. Okay, so that just kind of gives you an example of how we would go through and look at different problems, and we have to make sure that you understand all the concepts involved. And so we do a complete review of all of the concepts that are going to be on this year's AP Physics test. Okay, some other things that are unique to the AP Physics 1 test. There's several question types that are specific to AP Physics 1 and 2. And so one of them is the paragraph length response. So I have here, there's a question about, an oscillator, and there's kind of some wave stuff in here too. The one phrase that I wanted to point out in this is in a clear, coherent paragraph length response. Okay, so there will be a question on every test that is a paragraph length response, and so what they want is a paragraph structure that demonstrates that you understand basically what's going on here. So this is fairly typical in that they'll have some kind of introductory prompt where they'll set up the situation, and then they'll give you kind of a starter question that's worth like 2 out of the 7 points would be for part A. Okay, so here we basically have an oscillator that's oscillating this string and creating these standing waves, but there's a little twist in it too that the AP test likes to do. Little twists like that, where they take a problem that you've seen before and you definitely know how to do. In this is kind of, I don't think they're going to be covering this topic on this year's test, but in normal times they would usually have a section on waves, right? So you're used to seeing standing waves and stuff, but they'd say, okay, well, what if we have some standing waves, but they're different lengths? Do you understand the physics of that? Do you understand what's going on and why that may be the case? Okay, so the figure above shows a uniformly thick rope hanging vertically from an oscillator that is turned off. So when the oscillator is turned on and set at a certain frequency, the rope forms the standing wave shown above and right. P and Q are 2 points on the rope. So the tension at point P is greater than the tension at point Q. Briefly explain why. Okay, so you see the twist there. So usually when we do systems, we operate on the assumption that like the tension is the same at every point in the rope. And they're straight up telling us here, okay, no, the tension is not the same at every point in the rope. The tension is different. Why would that be? And so obviously you have to figure out that that's because of gravity and because it's a vertical rope, and especially because there isn't, usually when we do those kinds of problems, there's like a heavy mass at one end, right? And so compared to the mass of a 10 kilogram mass, let's say, the mass of the rope isn't that much. But when our only mass is the rope, then it does make a difference at what point of the rope you are, because you're going to have, twice the tension at the bottom as you would at the top, for example. Well, twice the tension at Q as you would at P, let's say. And so then you have to explain that, okay, it's because it's gravity. And then we go into the paragraph length response. And so they want a student hypothesizes that increasing the tension in a rope increases the speed at which the wave travels along the rope, which from what we know about waves, that sounds like an appropriate hypothesis. Okay, in a clear, coherent paragraph length response that may also contain figures and or equations, okay, explain why a standing wave shown above supports the student's hypothesis. So they say it can contain figures or equations, but it cannot be just figures and equations. There's almost always a point simply for writing a paragraph. So even if you write nonsense, you could get at least 1 point just for writing a paragraph, as long as it fits that form. You would not get that point if you're just writing equations and stuff like that. And sometimes you're not even, they won't even read your response unless it's in the form of a paragraph. So it's very important that you're able to follow those parameters. So let me give you an example of the grading rubric that they would use on this question. So again, like I said, it's usually 2 points for the first prompt and then 5 points for the paragraph. I've seen some where they have just 7 points for the paragraph, but that's very rare. So here they give 1 point for indicating that there is more rope or weight below 1 point than the other. So basically, some kind of indication that you're talking about weight. 1 point for indicating explicitly or implicitly. So you don't have to use their exact words, is basically what they're getting at there, but you'd have to somehow imply that the tension at any point counteracts or supports the weight below that point. So basically, if you just talk about how the weight at point Q is less than or is double the weight at point P because there's twice as much rope below, and therefore there's twice as much weight due to gravity, that would get you both of those points. You don't have to use their exact words. And then 5 points for the paragraph. Now, for the paragraph, this is probably the I would say the hardest place to get points for most students. It doesn't have to be if you kind of know how to state your point. And again, you don't need to get all 5 points in order to get a 5 on the test, right? You just need to be able to show that you know a bunch of the important concepts that they do. And if you explain yourself in a way that covers the important concepts, I would be very surprised if you don't get 4 out of those 5 points. Like it's fairly common you miss like one little thing. Maybe the grader doesn't see how you hit every single little thing, but your overall grade is going to be good if you make sure you're covering the important concepts. Okay, so in this case, 1 point for indicating that the wavelength is longer near the top of the rope or shorter near the bottom. Okay, so you don't even need to, that isn't even something that you would need to bring in outside knowledge. That's just citing important evidence, right? So you're citing what you're observing in the problem. Okay, so I cite that the wavelength is shorter near the bottom. Okay, so that's indicating that the tension is less at the bottom, as we referred to in part A, and therefore I'm seeing a shorter, slower wave, shorter wavelength. Okay, for indicating explicitly or implicitly that the frequency is the same throughout the rope. Okay, so explaining that that the frequency comes from the generator and not from any other aspect of, nothing about the rope affects the frequency. It's only the oscillator at the top. 1 point for using the wave speed equals wavelength times frequency. So somehow applying that that relationship to show based on what you already know, the things I already mentioned. That okay, so that relationship exists. And a point for indicating explicitly or implicitly that, as stated in part A, tension is greater near the top of the rope. Okay, so you can see that point 1 and point 4 here are very similar together, or very, very close together, right? So, just stating these things, you could get all of these points in maybe like 2-3 sentences, right? Which would qualify as a paragraph. You just have to be very careful. You want to state everything that you know, because it is so open-ended and because you don't know exactly what they're looking for in their points. You want to state everything you don't know. You just want to be careful not to state anything that's false, because if you state things that are false, then you may go backwards. You may lose points, but you want to make sure that you state everything that you know is true, because you could get points on any of it, because they don't necessarily tell you they don't tell you upfront necessarily what you're going to get points for. Okay, so that's the paragraph length response. Oh yeah, so I wanted to highlight that there's they give you a point here, right, for sufficient paragraph structure. So what does that mean? Basically, it basically means that there's a paragraph, right? So you would want like introductory sentence, your information, a concluding sentence, and that would be plenty. It doesn't have to be, like a 5-paragraph essay, right? They're not grading you on grammar or spelling or anything like that. It just has to be that you can demonstrate that you are able to reason not just in equations but also in English. Okay, and so if you can do that, then you'll get that point. Even if your physics is completely wrong, you'll still get 1 point. Okay, so another question type is the experimental design. So you see this is a 12-point question. It tends to be long, it's longer, you have more time. This is one that typically students do pretty well on, but me personally, I'm kind of worried about it this year specifically because of schools being shut down in a lot of places. There is a lot of students don't have access to the usual laboratory environment that they would. And so specifically things like designing experiments may not be taking place in their high school classes the way it usually would, which creates an extra challenge when you're trying to design an experiment and you don't have the background in doing as much of that hands-on stuff yourself. So here's an example from a past test. So a student wants to determine the coefficient of static friction between a long flat wood board and a small wood block. So describe an experiment, okay, for determining the coefficient of static friction between the wood board and the wood block. Assume equipment usually found in a school physics laboratory is available. So you can see how, okay, describe an experiment. So one of the skills that you would hopefully want to learn in your high school physics class is, okay, how do I not just perform experiments, but how do I create them myself? Because it's kind of a different mindset that you have to get into. It's like, okay, well, how do I create an experiment from scratch? Sometimes they'll ask you like a few different bullet points here. Like here they ask you, okay, first draw a diagram to describe the procedure. That's not always the case. They sometimes just say, okay, describe an experiment, describe, and they might ask you to do different parts of the experiment. So like, oh, specifically focusing on, this aspect of it for a different question. Here they specifically want a diagram. Okay, so draw a diagram of the experimental setup, okay, of the board and the block. That's just to kind of show, okay, here's your board and block setup. And then describe the overall procedure to be used. Now, a lot of students, you kind of grow up learning different ways of creating a lab report and all that. Most students are used to doing like numbered steps and stuff like that. You don't actually have to do numbered steps in your procedures for this test. It's allowed. You can do numbered steps, but it's also okay to just kind of in paragraph form or in a narrative explain what you would do or what the experimenter would do, going through step by step through this through this procedure. So okay, so you would you'd set up this wood block, and you'd put weights on top of the wood block and drag it or whatever. But you basically explain, okay, I'm going to do this and then I'm going to do this, and that can be in numbered steps or not. So then again, I want to look at the grading rubric for this, just so you can see kind of how they score these. So for A, so A was the well, this is all A, but A part point 1 was drawing the diagram. Okay, so for a diagram of an experimental setup to measure the coefficient of friction, so that is feasible in a school physics lab. Okay, so anything that you could feasibly use to measure the coefficient of friction would get you a point, even if everything else is wrong. Okay, at least if you can, like, if your diagram's like, okay, I could feasibly use that, they'll give you a point for that. Now, in a school physics lab is kind of there's kind of a big window there. Okay, so that could be anything from meter sticks and stopwatches to photo gates and motion sensors and stuff like that. And those are kind of the stuff that you might not have as much access to this year, and so you might not be familiar with how that kind of stuff works. But there's almost always a low-tech answer and a high-tech answer to every question about how you could do that. And so if you're not familiar with the high-tech answer, then just go with the low-tech answer. Even if like a meter stick and a stopwatch can usually do the same thing that a photo gate or a motion sensor could, it's not going to be as accurate, but you're not necessarily being scored on whether or not you have the most accurate experimental setup possible. Just, are you going to be able to take good data on this, and do you understand the limitations and experimental error that's going to come out of that? Okay. Another point for indicating the measurements necessary for calculating the coefficient of friction. Okay, so do you know not just what the experiment should look like, but how to take data out of that? Okay, and then one point for indicating equipment necessary for measuring the quantities required to calculate the coefficient of friction. So, have you indicated, okay, here's where the block goes, here's where I'm placing my masses, here's where my spring scale goes, and making sure that you're showing explicitly that these are the pieces of equipment that I'm using. That's not just like a scratchy diagram with some pictures on it, and it's like, okay, is that a spring scale? Is that just a piece of string? I don't know. It's clearly labeled, all that stuff, to make sure you get all of your points in those areas. All right, and then for our description, so you can see in this case, actually the diagram is worth as much as the description is, which usually, you get a lot more points for your description. But anyway, 3 points for a description that is consistent with the diagram part A. So let's say there's some kind of like horrible flaw in the way that you created your experiment. Okay, there's basically you set it up, you're in the testing mode and you just kind of get flustered and forget about the fact that you have to actually measure the mass of the wood block or something like that. As long as you are consistent with the mistake you made above, so you're not just like changing your mind halfway through and being like, now I'm going to be measuring it on a slope, and you change your experimental design so your experimental design doesn't agree with your diagram or something like that. Then you can still get the rest of the points. So your flaw that you had up above is going to cost you 1, maybe 2 points, but it's not going to cost you for everything down the line. You just need to make sure that you are consistent and show that like you understand how to do these other things. You understand how to set up like the procedure. You know how to set up the procedure based on your initial diagram. Then you can still get those points later on. Okay, so you also get a point for description that is conceptually valid with the methods to find quantities that would allow calculation of a friction coefficient. So that's kind of like one of the points above. So, but this is more mentioning that you know how to do, the concepts involved more than the implementation. And then 1 point for indicating a valid method for reducing experimental error. Okay, and there's always a point for reducing experimental error. Basically, and it specifically says that point, it has to be something beyond just repeated trials. So which repeated trials is good, but it has to be something like, okay, in the case of the wood block, maybe I use multiple different masses on the wood block. Okay, so that sounds like it's doing repeated trials, but you're doing repeated trials with a different basic, like you're changing a variable, right? And so by doing that, and it could be something that could reduce error or just account for it. Like using different masses would account for some kind of, small experimental error, let's say in the wood block, the mass of the wood block, or, something like that. Or it could be some way that you're reducing it by, using a photo gate instead of a meter stick in order to try and make this data as accurate as possible. But you have to somehow address that in order to get that point. And that's always the case. And then from here, it's a 12-point question. You see I've gone through 6 points here. The other 6 points would always be for some kind of data analysis. Sometimes they do the data analysis first and then do the experimental design part after that. The analysis could be somehow manipulating equations. It could be using graphs. A lot of times fitting a graph, something like that, which I find are things that students tend to understand a little better than the experimental design itself. But basically, you're looking at, okay, building those skills, and how do we? There are lots of different skills that you need to make sure that are very well addressed. And so we'd go through and do those, because they're going to be different on every question. So not every question is going to have all of those skills involved. But by doing a variety of questions, we can see where everybody's at on those. Okay, and the last question type that I wanted to address. There we go. Is the quantitative qualitative reasoning question. So this is kind of a question type that's very what do I want to say, unique to the Physics 1, Physics 2 tests, in that basically what they want you to do is they want you to be able to reason in quantitative, that would be equations, graphs, that sort of thing, and qualitatively. Do you understand qualitatively how things are going to play out? Are you able to hear somebody explain stuff and say, that doesn't seem right based on what I know about physics? Okay, so for example here, okay, so we have I cropped out the kind of the middle of this question, so it doesn't really make sense, but specifically what I want to focus on is this question type here. So the part B1 says, okay, which aspects of the student's reasoning, if any, are correct? Okay, which aspects of the student's reasoning, if any, are incorrect? So this is a very common type. They don't have this on every test. Sometimes the quantitative qualitative takes a different way of looking at things, but it's fairly common. Okay, so can you read through this paragraph and pick out things that are correct and incorrect? So not just to say, oh, the student is wrong, but to say, well, their student is correct in this, but I would disagree in this, right? Okay, so in this problem, basically you have a block that compresses a spring, and the block is released, and it travels down this path that has friction on it, and it says now it's compressed twice as far. Is it going to travel? So the student predicts that it'll travel 6 times as far. Okay, and so you have to look at, okay, what about their reasoning is correct, and which aspects are incorrect. Okay, so the student reasons that since the spring will be compressed twice as much as before, the block will have more energy when it leaves the spring, so it will slide farther along the track before stopping at position 6D. Okay, so you would say, okay, the student is correct in that compressing it further would give it more energy, and therefore it's going to travel further. Okay, but you'd say that maybe they're incorrect in that, twice the distance doesn't correspond to 6 times the energy, because we'd be reasoning that, right, this is based on elastic potential energy, and therefore it's going to scale as, basically x squared, so 2d. So if we went twice the distance, we would get 4 times the energy, so it would considerably go 4 times as far, right? And then we see part C says use quantitative reasoning, okay, including equations as needed to develop an expression for the new final position of the block. So express your answer in terms of D. Okay, so part B, we used qualitative reasoning. Okay, I explained that, okay, they're correct in this, but they're incorrect in this, and that's just I don't have to justify myself with equations or graphs or anything like that. I just have to explain, use from the paragraph that they gave me. I have to cite evidence saying, okay, this is what I observed is correct and incorrect. Then for C, they want me to do it myself. Okay, how would I solve these equations? How would I derive an equation? Okay, so there's the quantitative and the qualitative, and then so we see in D, explain how any correct aspects of the student's reasoning from part B are expressed by your mathematical relationship in part C. Okay, so now we have to tie the quantitative to the qualitative, and demonstrate that I can cite from my equation how how these things are related. Okay. Explain how your relationships in part C correct any incorrect aspects of the student's reasoning identified in part B. Okay, so I just showed in my equation that I just derived that this is why the student was incorrect about the distance. And I can show that from this equation that I just derived. Okay. Yeah, and then refer to the relationships you wrote in part C, not just the final answer you obtained by manipulating those relationships. Okay, so they're asking you to refer not just to your final equation, okay, but to the equations that you use to derive that equation, because the equations that you started with, right, are the ones that demonstrate the real relationships. The ones that you derived demonstrate that you can do algebra, but they might not necessarily demonstrate that you understand the physics involved. So you have to explain that you understand the physics involved, explain how that relates to the original prompt, and how that relates to the equations, because that shows that you really understand the physics. If you can go between the real world evidence that you observe and the equations that you see on paper, then you're really doing some physics. Okay. So that's all I had for kind of demonstrating the different question types and how we would go through and analyze these. At this point, if anybody has any questions, open it up to any questions you have about Physics 1 or the classes that we're offering, or anything related to that.
Hey, Colin, do you have any tips to share with our attendees?
Sure. Yeah. Just some kind of general tips. I kind of mentioned a little bit at the beginning, but just making sure that you're focusing on not just understanding the concepts as you're preparing for the test, but making sure that you understand the different question types and how to address those skills. Making sure that you're looking at different past tests, that have occurred, so we can make sure that we understand. Okay, how are they awarding points for this type of test? How do they award points for this type of test? So that when you see this year's test, you don't say, okay, I've never seen a question like this, because there's no way to predict, what's going to be on the test. There's no way to predict, are they going to ask, two different force questions and energy question? There's no way to predict. Kind of like, you get an idea that they're going, they always spread them out between different topics, and they always, spread them out between those different question types that I mentioned. But there's no way to guarantee, okay, they're going to be this and that. So you have to be prepared for anything, essentially, which means, knowing how to use all these skills that they're looking for, whether or not you hopefully learn them in your high school class, but different teachers have different styles. And so they might emphasize different things. And you have to make sure that you understand, okay, this is how to do each of these question types. This is how to, derive an equation. This is how to do a linear regression on a piece of data, so that I can, derive information out of that. This is how to cite evidence from the paragraph that they give me. If you know how to do those kinds of things, then you'll be okay. Even if you have, little tiny holes in your concepts, you'd be better off than knowing all the concepts and not having those skills, because that's really where the majority of the points come from, is from knowing those skills and knowing how to apply them correctly when you're going through free response questions, which are half the points for the test. So,
hey, Colin, could you share a little bit about what your class is like?
Yeah, so in the class, I think the number of classes and all that kind of depends on what people, how much demand there is for that. I think, but basically what we would do in a typical class is we would review a couple of units in, say a 2-hour class period. We would review a couple of units. Let's say we go over kinematics and forces during the first class, let's say. Then we would go through and do a bunch of practice problems on those courses. So, here I'd give you a problem, you would have a chance to do it, and then we'd go through and score that problem. So whether that be the multiple choice kinds of problems, where it's just like, okay, here's the problem, here's the right and wrong answer, because that's either a point or not a point, right, for the multiple choice. But then for the free response questions, we kind of dive into that and carve those out. And so you get the confidence of knowing, okay, I would have gotten 4 out of 7 on this problem. So that's, so that's okay, but I would like to get a 5 on the test. So how do I get, 5 or 6 points out of 7 on each one of these questions? Okay, so we go through and make sure that you understand, okay, this is what it's like. And I think for a lot of students, you're kind of a light bulb goes on when you do the grading, when you start actually grading these yourself, where it's like, okay, I'm grading my own responses and I'm seeing, oh, this is how I get all 7 points on that paragraph length response. Okay. Oh, I missed a point here, but like I said, 6 out of 7 is okay. That's still a 5. So then it takes away that worry aspect of going, am I a 2 on the physics test? Am I a 5 on the physics test? I don't know. But as you go through and kind of take those tests, it can kind of relieve a lot of that stress. So you can go into the actual test more confident. So I like to review the concepts, so we make sure, because some stuff that happened back in August, September, it's easy to forget little things that. So we review all the concepts, and then we go through and do a lot of practice, because hopefully you've taken a AP physics class, and so you've at least seen all the concepts before. But you may not have seen the specific test types. You may not have seen these questions. And so we focus on the practice stuff, but there is some conceptual review of the different concepts. And then we go through and do a lot of practice with all of the different question types, and multiple choice, as well.
Okay, thank you, Colin. Okay, I think that's it for today. I hope everyone have a good weekend. Thank you.